Alright, so this is our honors chemistry lesson video for section 5.1. And so now that we've learned about the structure of the atom in chapter 4, we are going to focus more on the electrons. What is going on in the electron cloud? The nucleus is pretty straightforward. You got some protons in there, you got some neutrons in there. But the electrons, it took a while to kind of figure out what exactly are they doing, where exactly are they, besides just saying, oh, they're somewhere in the electron cloud. So let's look into that. So the Rutherford's model of the atom did not really explain how an atom can emit light, like if you heat it or electrify it, or the chemical properties of an atom. So if you remember from chapter 4, we learned about J.J. Thomson's plum pudding model, and he thought there was a big positive force-filled area with electrons throughout. And then Rutherford did his gold foil experiment and discovered, oh, wait a minute, there's a nucleus, and the electrons take up most of the volume, but his model didn't really kind of say what they were doing. You know, it just said, oh, they're out there. So we needed to get a little more specific than that. So Niels Bohr studied the hydrogen atom because it's the most simplistic. Most isotopes of hydrogen have one proton and one electron and no neutrons. That's the most common isotope. So it's the easiest to study because you just have one proton and one electron. So Bohr proposed that an electron is found only in specific circular paths or orbits around the nucleus. Each possible electron orbit in Bohr's model has a fixed energy. The fixed energies an electron can have are called energy levels. So he started kind of organizing where the electrons were. And so he made these energy levels, and so he said that an electron can be at a specific energy level, but it can't necessarily be in between. Like it's either on the level or it's on the next level. And so he's the first one to kind of come up with that idea of energy levels. So the energy levels get closer together as you move farther from the nucleus, and the energy levels also get higher in energy as you move farther from the nucleus. So energy levels are kind of like a ladder. As you climb higher on a ladder, you get more gravitational potential energy because of your height. As you go up in energy level, when you're an electron, you have more energy to remain at that level. However, it's a little different than a ladder because in most ladders that I've seen, the steps are equally spaced. Well, energy levels, as you get farther from the nucleus, they start getting closer and closer together. That's important when we start talking about order of sublevels in section 2. So electrons can actually jump from one energy level to another. And a quantum of energy is the amount of energy required to move an electron from one energy level to another. So if an electron's on the first energy level and it gains a quantum of energy, it can jump to the second energy level. If it gains more energy, it could jump to the third. If it gained enough energy from the first energy level, it could jump all the way to the third. The way it falls back down is it loses energy. So if it wants to fall back down to the second, it has to lose energy. If it needs to fall back to the first, it has to lose more energy. Okay, so electrons can move between the different energy levels. It can go from first to second, third, so forth and so on. But energy is required to do that. So an electron must gain energy to jump to a higher energy level. And when an electron has jumped to a higher energy level, it's called the excited state. So you jump up when you're excited, and so do electrons. An electron must lose energy to fall to a lower energy level, and when it's at the lowest energy level possible, it is called ground state. Now, ground state is not necessarily the first energy level. If the first energy level is full already, ground state may be the second energy level. If the first, second, third, fourth energy levels are already full, ground state may be the fifth energy level. It's just the lowest energy level possible for that specific electron. Everybody can't fit in the first energy level. It only holds 2. So it's just the lowest possible for that electron. So Bohr had some postulates when he was doing all of his studies on the hydrogen atom. And so the first part is hydrogen's electrons can only exist in orbits of certain radii, which correspond to specific energies. So here is his energy level idea. The second part is an electron in a permitted orbit has a specific energy, hence the reason we call it energy levels. It will not radiate energy and therefore will not spiral into the nucleus. Okay, because the whole thing is, technically, electrons, which are negative, should be attracted to the protons, which are positive, so why doesn't it just attract to the nucleus. That's the whole, what's going on there. Well, because it has that energy, it will remain in its energy level. And then the third part is energy is emitted or absorbed by the electron only as the electron changes from one energy level to another. The energy is emitted or absorbed as a photon, and then we'll talk about this formula later. E equals h times nu. E is energy, h is Planck's constant, and nu is frequency. So we'll talk about that when we start talking about the wave properties of an electron. So Bohr's model restrictions. Bohr's model was not perfect. So Bohr's model accurately describes the movement of an electron in the hydrogen atom, but it cannot describe the movement of multi-electron atoms. Well, yeah, hydrogen is the only atom that has one electron. That means all other 117 elements are multi-electron atoms. And his model does not describe the movement of electrons as well in those. So, he's at less than 1% correct right there. However, he did come up with two very significant things that we still use today. The first one is electrons exist in specific energy levels. And then the second part is energy is involved when electrons move from one level to another. So although his model was very accurate for hydrogen, it kind of falls apart a little bit on the multi-electron atoms. But these two ideas are what we still use today. Even though our most up-to-date model is not necessarily Bohr's model, we still use his ideas. So what is our most up-to-date model? The quantum mechanical model. So the quantum mechanical model of the atom is based on the mathematical probability of the location of electrons using the Schrödinger's equation. Now, we are not going to use this equation. We're not going to do anything but basic algebra. So you're just going to have to trust that all these shapes that seem really weird that I'm showing you, they were all mathematically calculated. So that's where they're coming from. If you want to take upper level chemistry in college, you will use this formula and you can actually build the models yourselves through graphing. The quantum mechanical model still has energy levels, just like Bohr's model, but the exact path or orbit of the electron is unknown. So we're not saying like it's going to orbit in the same exact radii. We're just going to say there's an area that the electron can be in when it's in that energy level. So since the quantum mechanical model is based on the probability of finding an electron, then the orbitals are normally shaded with a fuzzy edge. So it's based on a mathematical probability. So it's kind of like just this array of dots. So the nucleus would be in the middle, and you can see there's a lot of dots really close to the nucleus. And as you move out, the dots start getting fewer and fewer. That's because, of course, the electron's most likely going to want to be near the nucleus. So like I said, a lot of times it's drawn as shaded or with a fuzzy edge. An atomic orbital is the region of space in which there is a high probability of finding an electron. And so, of course, in this one, it's more likely to be found near the nucleus than further from the nucleus, due to the shading. So within the border of an atomic orbital, there is a 90% chance of finding an electron. We can't go all the way out to 100, or our orbital kind of never would end at that point. The darker the shading of the orbital, the higher the chance of finding the electron. And so here's just another example of the dot model. A lot of times you'll see it look more like the one on the next slide, though, instead of an array of dots. So let's just review our 4 atomic models. So first we had J.J. Thomson's plum pudding, the positive area with the electrons. Then Rutherford discovered the nucleus, so he put the nucleus in the middle. Electrons are just somewhere around it. We have no idea where. In Bohr's model, we have our nucleus, and then we have electrons in specific energy levels. But they can jump to different energy levels. So I'm showing this electron can jump to the next energy level. How? If it gains energy. And then last is the quantum mechanical model. So we still have that positive nucleus in the middle. And so you can see that here the orbital just kind of fades away. All right, it's darkest here where you're most likely going to find the electron. And then as the probability fades, the shading fades. And within the border of this, there's a 90% chance of finding an electron. So let's focus more now on this quantum mechanical model. So we, in the quantum mechanical model, have, let's see, like figured out a lot more about energy levels than Bohr first thought when he came up with them. And so we have energy levels, they can be broken into sublevels, which can be broken into orbitals. So we're going to talk about all of that. I'm going to go ahead and tell you, it's going to be somewhat confusing at first. You really need to watch the lesson videos for section 5.2 to kind of clear up what I'm going to end 5.1 with, because otherwise it's very confusing. And that's totally normal though, just saying. All right, so let's talk about some energy levels. Each energy level can be composed of multiple sublevels. Energy levels are assigned a number from 1 to 7 based on the row on the periodic table. So there's 7 periods or 7 rows on the periodic table. There's 7 energy levels. Each sublevel can be composed of multiple orbitals. The sublevels are assigned a letter. And so you have a choice of S, P, D, F, or G. And then each orbital can hold a maximum of 2 electrons. So it's kind of like an orbital is a queen-size bed. It can hold 2 people. You can have multiple beds in a room. So we could say a sublevel is a bedroom. And then you could have multiple sublevels in in an energy level. So we could say that the energy level is like the house. So the energy level is the house. You can have more than one sublevel, or you could just have one sublevel. Some houses only have one bedroom. So sublevel is like a bedroom, and then each orbital is like a bed that can hold at most 2 people. All right, so let's look a little into what do the sublevels look like. So remember, y'all, this is all mathematically calculated. That's why the shapes are about to get super weird. So first is the S sublevel. All S sublevels have 1 orbital and can hold at most 2 electrons. Every single one. It doesn't matter if it's 1s, 5s, 7s, 2s. If it says S, it has 1 orbital and can hold up to 2 electrons. The number in front of S represents the energy level. So like 1s is on the first row of the periodic table, 5s is on the 5th row of the periodic table. As the energy level increases, the size of the S sublevel increases, but it can still only hold 2 electrons. So like 1s might be this big, 2s is bigger, 3s is even bigger, but each of them can still only hold 2 electrons. It just means in 3s, those 2 electrons could just be further from the nucleus. And then an S sublevel, as you can see, has a spherical shape. And remember, this is 3 different S sublevels right here. All right, so let's move on to P. So all P sublevels have 3 orbitals and can hold a maximum of 6 electrons. So you have 3 different orbitals in a P sublevel. So this is what P looks like. And so it's comprised of 3 different orbitals. Okay, I know you feel like it's 6, but it's 3. Okay, you have the yellow one, this kind of bluish-green one, and the red one. And each orbital can hold 2 electrons. So since there's 3 orbitals, it can hold 6. The P sublevel has a dumbbell or teardrop shape. Each teardrop is referred to as a lobe. So each P orbital has 2 lobes. Okay, so this can hold 2 electrons. These 2 lobes can hold 2 electrons. This can hold 2 electrons, so it can hold a total of 6. And these all overlap each other, so it looks like this. But once they start getting complicated, like in the next couple of slides, I won't show them overlapped because otherwise it'll be overwhelming to look at. So I'll show them broken up like this. All right, so next is the D sublevel. All D sublevels have 5 orbitals and can hold a maximum of 10 electrons. So again, if you notice, each orbital can hold 2 electrons, so 5 times 2 is 10. So S had 1 orbital, 2 electrons. P has 3 orbitals, 6 electrons. D has 5 orbitals, 10 electrons. So hopefully you're noticing the pattern here. The D sublevel has a 4-leaf clover shape, which means it has 4 lobes, and they're just kind of pointing in different directions. So see, here's one of the orbitals, this one's an orbital, here's one, and they're all just kind of facing in different directions. Or one of the D sublevels has 2 lobes with a donut shape around the center. Okay, and again, all 5 of these would be overlapping each other, but we pull them apart so that you can see them better. All right, so D has 5 orbitals and holds 10 electrons, so F has 7 orbitals and can hold up to 14 electrons. And so again, you can see all 7 of the shapes right here. They would all be overlapping, but again, then we wouldn't be able to see what they look like. And so each shape can hold 2 electrons? And again, I know you're probably looking at these thinking, what in the world? This is all mathematically calculated, okay, based on Schrodinger's equation and what we know about energy. So the last one is G. So G has 9 orbitals and can hold up to 18 electrons. And so again, here's the pictures of those. We do not have enough elements to fill in the G sublevels yet. So in section 2, when I teach you how to do something called electron configuration, if you ever make it to the G sublevel, then you have done it incorrectly, okay, because we don't have enough elements. So you may think, well, how do they know what it's going to look like? Well, remember, it's a mathematical calculation. Like, I can calculate how long it's going to take me to drive from here to Atlanta without actually doing it. I can just calculate it. And so that's what's happened here, is they can calculate the probability of where the electron will be, even if we don't have an element that actually has that electron arrangement yet. So here's just a review of everything I just told you. So notice it just goes 1, 3, 5, 7, 9, and you always multiply your orbitals by 2 to get the number of electrons. Because remember, an orbital is like a queen-size bed, 2 people in 1 orbital. So you just got to remember the order, S, P, D, F, G. So maybe think of some sort of acronym to help you remember the order of that. All right, so let's knock out this section assessment. So why did Rutherford's atomic model need to be replaced? Well, his model did not explain how atoms can emit light or the chemical properties of atoms. Okay, so his model didn't explain how atoms can emit light or the chemical properties of atoms. So number 2, what was the basic new proposal in the Bohr's model of the atom? Well, there's actually 2. He discovered the fact that there are energy levels, and he determined that electrons can jump to different energy levels. Okay, so his 2 proposals were energy levels exist, and electrons can jump to different energy levels. So number 3, what does the quantum mechanical model determine about electrons in an atom? Well, remember, it's based on a mathematic probability. So it gives us a probable, like the probable location of where you would find electrons. It shows us the probability of finding an electron. So number 4, how do 2 sublevels of the same principal energy level differ from each other? So remember, the sublevels are like the S, P, D, F, G. So there's lots of different things about them. They're different shapes. You could say they have different numbers of orbitals. You could say they can hold a different amount of electrons. Any of those would be fine. So number 5, how can electrons in an atom move from one energy level to another? Well, they would need to either lose or gain energy. So if they want to move up, they would need to gain energy. If they would want to move down, they would lose energy. So they need to lose or gain energy. All right, so how many orbitals are in the following sublevels? So remember, don't let the number in front throw you off. All P sublevels have the same amount of orbitals. All S sublevels have the same amount of orbitals. So really, to answer this question, you're just basing it on this chart right here. Okay, so 3P has 3 orbitals because it's P. 2S has 1 orbital because all S have 1 orbital. 4P has 3 orbitals. So see, notice 3P and 4P both have 3 orbitals. The only difference is that the 4P ones would be the same shape, they would just be bigger. And then 3D, all D sublevels have 5 orbitals. And then 4F, all F sublevels have 7 orbitals. All right, so like I said, y'all, if you're sitting there after this very confused, that is totally normal. Okay, just power through and make sure you get through section 5.2 lesson videos. Once you get through those, then I kind of like tie all of it together, and then it gets super easy. Okay, most students do really, really well with this stuff, but nobody thinks they're going to when I first start going over it. So I'm telling you, just hang on, get through section 5.2, and then you'll think it's just as easy as I did.